Welcome everyone to ENTSO-E's Business Network for Innovation webinar that addresses today's smart grid worlds of innovation, dynamic line rating, which is one of the major tools for power system modernization. I'm very happy that we have in this 1 hour and 20 minutes webinar Guido, who is the chair of the committee of ENTSO-E, the research committee of ENTSO-E. We have Norena Constantinescu, who is the lead in ENTSO-E, the leading manager on research, development and innovation, sitting next to me. We also have Joanna Lepnitz, who is organizing these webinars since their very beginning. Many thanks, Joanna, for a very good job on now already. I think it's the third of those webinars attended by hundreds of people. We have Frederic Vassort, who is the CEO of Ampacimon. We have Jozua van Oosterom. He's from Energy Solutions. We have Victor Maire, planning engineer at the National Control Center of Elia. So we are very happy to have these very competent participants that I'm going to introduce in a bit more detail once their speaking time is up. And we encourage you at once to ask questions. Send us your questions, please. Target the speakers you want to address the questions to, or send us a comment and we try in real time to answer all these questions with you. So many thanks for your participation, and I hand over now to Guido, the chair of the committee, research committee from ENTSO-E, for his introduction on why we do these business networks for innovation, these webinars all together.
Thank you, Susan. I hope you hear me.
Yes, very well, Guido.
So I'm showing the slides. Thank you to all to attend to this webinar. I think it's very important because this is the third one we have organized within ENTSO-E, and in particular within the committee on research and innovation. So with the slides, I'm going to introduce the business network for innovation. Is very important because it allows us to create an ecosystem of energy transition players driven by business perspective. And so the idea is to put together ENTSO-E and the TSO, the committee of TSOs, with startup citizens initiatives, but also with opinion leaders, institutions, and the energy businesses. So in order to share the view, to understand what is to share what is going on, and also to try to work together. There are over than 130 members, and as I said, after the first two webinar had on a common grid model and energy data, and on storage, this is the third one on the dynamic thermal rating, one of the main important topics on the TSO side, let me say. I'm working for Terna, and let me say that we have a lot of, we think that dynamic thermal rating is very important because have a high potential within areas where we have a lot of wind generation. In Italy, all the renewable energy sources, but also the more efficient generation is located in the south part of Italy. And so it's very important for us to bring the energy from the south to the north. And the installation of this dynamic thermal rating helps us to push the energy from the south to the north, especially when there is a lot of wind, in order to avoid to cut the wind for congestions between the bidding zones between south and north of Italy. So as you can see, the dynamic in the slides, dynamic thermal rating assessment is achieved by cooperation of the single agent that communicate with the reduced numbers of surrounding elements by short-range communication link. Then we will have the players, the other speaker who will go in depth on these topics. Now, just to remind you, what are the next upcoming conferences within ENTSO-E? The first of all, for which I asked to register, is the Hanno-Gridi Events 2020 events. Is going to be held the 13th and 14th of May here in Brussels. And then we have also other two events. The one in the 8th October in Copenhagen is the conference among the different research security sectors. And the 12th and 13th of November, we celebrate the 10 years of ENTSO-E, 10 years of TSO's cooperation. Just to remind you, the next webinar is going to on business network innovation is going to be held scheduled for the 24th of April 2019, and is dedicated to the artificial intelligence and electricity. So also to use in this case satellite technologies and smart grid. Here you have the list of TSOs participating within ENTSO-E. So Susan, I finished my presentation.
The events, by the way, I forgot to introduce myself. I'm leading strategy and communication in ENTSO-E, and the research team is also part of this horizontal layer in the work of ENTSO-E. Now I'm happy to introduce Frederic Vassort. Frederic, you are the CEO of Ampacimon. That is a Belgium-based company. And what is Ampacimon? It is a provider of grid monitoring solutions for high and for medium voltage, for TSO and DSOs in that sense. Yeah. And you are in particular developing dynamic line rating products, and you are even having the global leadership position. We are very proud of you being in Belgium, where we are as well. Frederic Vassort has been leading Ampacimon since 5 years, and prior to that, he has led a number of industrial global businesses for a US diversified industrial company, spent working for ENGIE, the former GDF, in Asia, Schlumberger for energy meters, and has had various assignments in Europe and in Asia. Frederic is an electrical engineer with an MBA, graduated in France and in Singapore, and now he's living here in Brussels. So Frederic, we are very keen to understand from you, what are the benefits, the risks, and the future applications of dynamic line rating? And you have 15 minutes to present your views. Thank you, Frederic.
Thank you very much, Susan, for the introduction. So indeed, I'm the CEO of Ampacimon, which happens to be based in Belgium. That's a coincidence, but Belgium seems to be at the center of innovation when it comes to grids technology here. So indeed, I'm going to talk today about the way to use DLR, and in particular, how to integrate it on grids and show what value it can deliver in various applications. So Guido made a very short introduction about it, but let's go into the basics of DLR. What are we talking about here? So DLR is a technology that tries to deliver more capacity of existing lines, and I'm talking here specifically of overhead lines. The next presentation will talk about underground cables where similar concepts can apply. So an overhead line typically is constrained or is limited in its thermal capacity by its maximum temperature, the maximum operating temperature of the conductor, or by the maximum sag, which is determined by the maximum distance, minimum distance to the ground, so that a spark is isn't created, a fault isn't created between the line and the obstacle on the ground. Normally, in normal circumstances, most of the grid operators today around the world still use static ratings, which are determined by worst case situations. So basically, we would assume that the line would expand because of the load, that's a Joule effect, and then it would be cooled down by the prevailing weather parameters. And TSOs would typically assume worst case situations, so maximum ambient temperature, no wind speed assumption, high solar radiation, to determine the capacity of the line. DLR, conversely, is trying to achieve that in a dynamic way, hence the name dynamic line rating, by measuring the parameters that influence, that impact the capacity of that line in real time. So if I go a bit more into the details, this is a graph that shows that a line indeed is subject to a number of influences. One is obviously the load, the current that flows through the line, that would have a tendency to warm up the line, to heat it up, and therefore to expand its material so that the sag would increase. The other influencing factor would be the ambient temperature. If the weather is warm, obviously the line would be warmer as well, and therefore would expand more. Conversely, if the weather gets cooler, the conductor would have a tendency to cool down and therefore to sag less. Same effect with solar radiation, and the most important one, the one that has the largest impact by a very significant margin, is wind. When the wind blows on a conductor, even at low wind speed, it would take out the heat that is generated inside the conductor and cool it down, and therefore reduce its temperature and reduce its sag. And you can see on the graph that I've inserted here at the bottom of the slide how that influence can be computed or simulated. And if you assume that a typical conductor would have a maximum operating temperature of 75 degrees. That's the example shown here. Typically, the rating would be determined assuming very low wind speed, typically 0.5 meters per second. The different standards, either IEEE standards or SIGRE standard, but they're very, very similar. Now, so that would result in this example in a capacity of, say, 1,000 amperes. Now, if you assume that the wind blows to only 2 meters per second, then you can see that the curves moves to the right-hand side, and therefore the capacity increases by 50%. If the wind blows to 5 meters per second, which is normally the type of wind that you see, which starts to activate wind turbines, the capacity doubles. So if you're capable of measuring all these parameters accurately, and that's a big if, and that's really all the science and the art that belongs to this technology. If you're able to measure those weather parameters, and most importantly the wind, accurately, you could actually free up a lot of latent capacity in a given line, and therefore in your grid. And that's what we want to achieve with DLR. Going to move to the next slide. Very good. So there are different DLR technologies that are available. I showed major categories here in this slide. I've ranked them by level of capacity gains that could be freed up, and conversely by the amount of risk, safety or security risk that the grid operator would be prepared to accept by using these various technologies. So one obvious one is simply to use weather models. Weather models would tell you what is the expected prevailing ambient temperature and the wind speed, and you could actually model those parameters onto the behavior of the conductor, and therefore theoretically calculate its rating. Now, the downside with that is that it's even though they make progresses, it's still difficult to be very precise in terms of weather modeling, and it's even more difficult to be precise at the level of a line, which is typically 20, 30, 40 meters high above the ground, and that doesn't exhibit the same behavior along all its profile. So that would give you some gain, but if you want to be safe, you would have to downscale quite a bit your DLR calculations to be safe. Next option is to be a bit more precise and to install weather stations along the line, which could give you a reading of the prevailing weather parameters on that line. But again, they would be as accurate as the weather station would be, and obviously it depends on the number of weather stations that you can afford to have along the line. And the more the better, obviously, but you will still not have any input on the true behavior of the conductor. So it's basically like an open loop system. Next option, which is more accurate, would be to have sensors mounted on the conductor itself, typically temperature sensor that would measure a temperature on the conductor. That would give you the same benefit as the previous ones, with the addition of having at least one parameter known on the behavior of the conductor, namely the temperature, but you would still be blind as to the wind speed and other parameters. And also what we've seen and what the research has shown is that the temperature of a conductor is very difficult to determine, because at best you would determine a point measurement on a very precise location of one span. We have seen that the variations of temperature from span to span and even within the span can be actually quite large. So therefore you would have to be cautious with that, and prudent operators would typically downgrade that information in order to calculate the rating. And then finally, last but not least, you have other categories of sensors, which we're proud to supply, but we're not the only ones, who would be directly mounted on the line and would measure a whole range of parameters, the temperature as well, but the sag also directly. There are different methods to do it, and also the prevailing ambient conditions seen by the conductor itself, and notably the wind. So if you're able to do that, then you have all the input parameters to calculate an accurate DLR value, and therefore make full use of it and make full use of its gain, while remaining completely safe and secure, because you permanently monitor the temperature and the sag. So if ever something wrong was to happen, and if ever we were getting too close to the maximum limit, we could raise an alarm. Sorry, it takes a little while for the slide to move to the next slide. So let's go into the applications now and examples of use cases. So I've shown here the value in euros that is spent, I would say wasted by the system, by the electrical system at large in Europe. This is data that goes back to 2015. And if you look at that, there are a couple of countries that have a lot of congestion issues that is well known in the industry. Poland, for example, but Germany as well, which alone spends in excess of 1 billion euros in congestion costs. So that translates into a lot of redispatch or curtailments. And if you can work out the costs of that, because it's public information, it costs approximately 23,000 euros per gigawatt hour of redispatching. So in that, if we look at one line in Germany, we took that example. This is a line that has seen quite a lot of redispatching in 2017 to the tune of 431 gigawatt hours of redispatched energy across that line, simply because it was congested. And as you know, Germany needs to carry a lot of wind farm produced energy in the north down to the center and to the south of the country, where the majority of the load is, and that creates congestions. Now, if you apply DLR on this line with a typical distribution of capacity increases that we see routinely in lines across Europe, we now have dozens and dozens of lines deployed and monitored. This is a fairly typical example of the distribution of DLR that you would see over a year. In this example, that's the green curve here. 50% of the time, so the median point is about 30 or 35% of capacity increase. So that's the median. But still, if you take the extreme of the curve, you would still gain approximately 15%, 90% of the time, and still 6%, 98% of the time. So the quasi totality of the year. Now, if you translate that into monetary value, into euros and cents, using the same example as before, in a typical days or in a typical congested day, you would have typically 6 hours of redispatch hours. That would allow you to avoid 1200 megawatt hours of redispatching at the same value as what I've shown before. That would save you 27,000 euros per day on one congested day alone. So knowing that a typical GLR deployment on a line, depending on the technology you want to use, is cost typically a few €100,000 per line, you would have recouped your investment in weeks. So we're talking about very quick return on investments here. Now, another example, if I manage to switch to the next slide, would be interconnectors between countries. This is an example of Belgium, which has faced in the past interconnection issues. They needed to import more energy because some of the nuclear plants in Belgium were shut down. So in that case, Elia decided to deploy DLR on all their interconnectors, and not only to monitor them in real time, which is already done quite routinely, but also to use forecasting in order to be able to use the projected DLR on the day-ahead market, the 2 days ahead market, in fact. And we have now software available. This is commercially available since several years, that tell you, based on sensors and based on weather forecast, what amount of capacity would be available on those interconnectors, for example, in up to 60 hours ahead. So therefore, you can use that on the market. And in this example, we've shown that if and we routinely do that, you can get only 3% of gain on the limiting lines. That would translate on 22% of gain on the whole cross-border exchange. And in that example, in 4 hours, you had saved to the system in excess of 200,000 euros. So again, we're talking about return on investments that are measured in weeks. And what I want to stress is that these systems are deployed within months. You don't need to wait years and years and years, just like you would do otherwise in a reconductoring or in a new line scenario. Last example, last use case is wind farms, and here we've chosen to talk about an example of offshore wind farms, which are built also in Belgium and North Sea. There's already approximately 800 or 900 megawatts of wind farm available. There are plans to increase that to in excess of 2,000 megawatts offshore. So significant investment to bring that power onshore. But once it's landed there, I would say on the coast, you still need to carry that power, all these wind generated energy, to the load centers. And here, I've zoomed in on one line that we've monitored close to the North Sea coast, where this line was actually already facing quite high flows because of simply the surrounding topology. And with the arrival of all these offshore wind farms, Elia had decided to deploy DLR on these lines in order to debottleneck the congestion and to facilitate the dispatch of the offshore wind energy. So that has been in place since several years. And what do we see on this plot here? You see that naturally when the wind blows, the wind farms generate, so the wind in-feed increases. These are the blue spots here on this graph. And at the same time, when the wind blows and generates more wind in-feed, you also have, and that's the vertical axis on this chart, you also have increased capacity of that particular line. This is represented here by the purple dots. So you can see that the extra capacity delivered by DLR allows to accommodate this additional wind in-feed that is produced by offshore wind farms. So by using a correlation between the fact that the line is cooled down by the prevailing winds, and at the same time those same winds would activate wind turbines and would generate energy, you can actually I wouldn't say you would avoid, but you can postpone reinforcement investments, and you can make do with your existing lines for probably a few more years than you would otherwise do, and start accommodating more wind farm connections to your grid, or avoid curtailment until your grid is structurally reinforced. So what are the takeaways from that? DLR is now well established. It's been around for years, but it is now really fully integrated into TSO's operations, thanks to connections with the SCADA, with the EMS, with all the tools that the grid management tools that TSOs would typically use. It comes not only with real-time options, but also with forecast options, so that you're not only looking at what's happening now, but you can anticipate actions. It is well proven in the use cases of traditional congestion management, optimization of interconnectors, optimization of wind integration with extremely quick paybacks. We are always talking about paybacks measured in weeks, if not days. So we're not saying, as I say, that it will replace new lines. New lines are still needed when the grid is severely congested, but it gives us an additional tool which is extremely flexible that TSOs can use, and that can be deployed very, very quickly. We're talking about deployments measured in months, that give them a new tool, very flexible, to increase capacity of lines while their more significant investment programs and infrastructure deployment plans are being put in place. So that concludes my presentation. I've shown here a few further trainings, the links that you can access, or tutorials that have taken place or that will take place if you want to know more about their subject. Otherwise, obviously, feel free to shoot questions and I will answer them and get back to you with more details. Thank you very much.
Many thanks, Frederic, for this very interesting presentation. And we are a little behind schedule. We will have a block of questions in the end. But before I hand over to the next speaker, I can't avoid asking you one question, which is, of course, dynamic line rating applies to AC technologies. You were mentioning this example of the offshore wind park in Belgium, and I'm just wondering, that must be AC then too? This
Yeah, the lines we're mentioning are AC lines, yes.
Exactly, because normally it's DC connected. I think it's important to say that because in the future we will see more and more like skeletons in the highly meshed system, these DC lines, and this increases certainly complexity on what you are doing. I can imagine, and of course a second point, the possibility to improve the available capacity to market on interconnectors is certainly one part of the answer, but not the answer on our 70% headache that is coming with the clean energy package. But let's take these questions back at the end of the presentations. And I'm now very happy to introduce our next speaker. And this next speaker is Jozua von Oosterom. Jozua, you are an electrical engineer at Energy Solutions in the Netherlands, working there since now 12 years. In the past, you worked on designing new power cable links for TSOs, but also for wind farms. In a moment, you are in charge of research and development of online monitoring systems for underground cable power cables. You have a master degree in electrical power engineering from the Delft University of Technology. So very happy to have you here in this interesting webinar and talking to us about how can we apply dynamic line rating in cables.
Yes, thank you. Good afternoon, everyone. I would like to just explain something about applying DLR in cables. My screen is visible, I hope. Is it?
Yes.
Yeah, it should be.
Yes, it's all fine.
Okay. So first I would like to explain a little bit about the abbreviations that are used in the industry for underground power cables and the difference between overhead lines. Most commonly used is the term dynamic cable rating, and it's also because to make the difference with overhead lines. With overhead lines, you have much different way of calculating dynamic rating capabilities compared to underground cables. With underground cables, you have a lot higher thermal capacitance of the surrounding soil you have, but also of the cable. And one of the challenges with designing new cable connections is that you cannot really know for sure the actual ampacity of the cable connection, because there are a lot of unknown parameters that can influence the rating of the cable. So the only way to really know the actual ampacity of the cable is to measure the temperature of the cable and perform calculations to verify the ampacity. And that's what in industry is also called a real-time thermal rating. So you have real-time data. You use it to calculate the thermal rating of the cable connection. So in the picture on the right, you see just an example of an underground cable single core. What we normally do is you make a thermal model of the cable itself. So you have a heat source, mainly the conductor losses. You have a thermal capacitance, and you have a thermal resistance of the insulation. And then you also have the environment part, which is also quite important, because when you have a new cable route installed, it goes through many of different lane configurations, and all these lane configurations must be modeled in thermal models to make sure you calculate the right thermal rating of the cable. So the thermal zones can be every zone where the cable is different, you need to model it as a separate zone. For example, if you have a road crossing where the cable is installed in a duct, you need to make a different zone. If it's in a horizontal drilling, you need to make a different zone. So all these zones you need to take into account when you make a thermal model for the complete cable connection. And it can be even only a zone of a few meters, because every few meters can be critical in the cable connection. So you can have overheating of the cable only on the very small part, and that's then the weakest link. So it's very important to model everything correctly. Still, one of the quite unknown parameters is the thermal resistivity of the soil, which can change during the season. In difference with overhead lines, underground cables are not really directly influenced by the weather, but indirectly it is due to the surrounding temperature that will vary during the season. So to verify if this is working, if you calculate the right values, you use a model from the IEC, but also a verification loop to just calculate the temperature response. And the calculated temperature response is verified with a temperature that is measured on the cable. And if there's any difference between the measured and the calculated temperatures, then you need to muted the thermal resistivity in the model or the surrounding temperature. Or there could be something else happening that needs to be investigated. But one of the very important parameters to have is the measurement data from the temperatures. With older cables, there's no temperature sensor installed. So what you can do is install at a hotspot a measurement pole that's installing with temperature sensors on the cable. So you need to dig up the cable, place the temperature sensors, and install the measurement pole. This is just an example for using with a 4G modem and a solar panel. So it's operating by itself and sending the data through a server where all the calculations are performed. But the better solution, which you can do with modern cables, is use distributed temperature sensing. Distributed temperature sensing uses a fiber optic that is integrated in the power cable to measure the temperature response. And there are basically two technologies that are used in the industry. It's the Briouin technology and the Raman technology. With the Raman technology, you basically send a laser pulse into the fiber optic, and you get some reflections which break up into two different parts. one of the two different wavelengths. One wavelength is not influenced by the temperature, but the other wavelength is. So if you have a different intensity, you have a different temperature, and in this way you can measure the temperature of the power cable along the complete cable length. The BRION technology uses a frequency shift in the signal that is sending, and basically the main difference between the two is that BRION is used for longer ranges because it's less influenced by the length. But the Raman system has a limited range because the farther away the pulse goes, the less reflections you get. So how does it look in practice? These are two examples of underground power cables. On the left one you see a single core cable with the fiber optic integrated under the metal sheet. You cannot place the fiber optic in the core because that's just not possible. But in the end, what you want to know is the temperature in the conductor, because that's the limiting factor in the cable. So the way you do this is you use the thermal model to calculate this temperature back, and it's not a fixed temperature or between the fiber optic and the conductor, but that's varying on the load. So that's why it's important to have a thermal model to do these calculations. For submarine cables, it's basically the same, but you have it on a bit different position in the cable. So how does this look in practice? This is just an example of a temperature measurement on an offshore wind farm where the temperature monitoring system is installed on the platform. You can see the temperature in the SCADA room, and when the fiber is getting out of the SCADA room on the cable deck, you can see the temperature drops to the ambient temperature outside. Then it goes in the power core in the J-tube. The J-tube is the vertical part where the power cable is installed that goes on the water. And above the water you can see a very high temperature peak. And that's what you would expect normally, because here the J-tube is filled with air. And air is quite a good insulator, so thermally. So that's what you would expect, but there is also some convection in the J-tube. If the J-tube enters the water, you can immediately see that the temperature drops because it's cooled by the seawater. And then you have what we call a cable protection system, where the cable goes into a bend out of the J-tube into the cable seabed, which is also some insulating material. So this is just an example to see that you can very accurately measure the temperature in the cable. This is an example of a load on the cable from a power plant. There are 3 horizontal drillings in the cable. At the end of each horizontal drilling, there is a peak in temperature, and that's because the rest of the drilling is filled with water, but at the end there are some air pockets, and these are quite important also to take into account, because these can be a limiting factor in the cable connection. Distributed temperature sensing is already quite a known technology and is used for a very long time now. This example is already almost 10 years old. And the last few years, we've seen some examples where it really has been useful to use dynamic cable rating in underground power cables. So I would like to just briefly go through 3 of the practical examples we have experienced. One is on an overload on a 150 kV cable during a fault on another cable. The second one is from a wind farm, and the third one is a thermal problem also on the grid connection cable. So the first example was there was a fault in a 150 kV cable connection in one of the circuits. This was indirectly connected to a lot of offshore wind, and in the picture on the right you can see the continuous current limit in red. And the orange one is the load that actually happens during the overload. And the blue line represents the measured temperature of the fiber. This was on the most critical part in the cable connection. And what you can see that there is still a lot of room in temperature. The maximum fiber temperature for this cable was about 50 degrees, which in this case represent to a maximum of about 70 degrees conductor temperature. And 90 degrees was the limit for this cable. And you can see that the load was for multiple days above the continuous rating. And because of the large time constant of the cable, it was not a problem to overload this cable this much. And it really helped to avoid having extra costs to reduce the power. For the cable point of view, it could even has been higher, the load, but in practice there can also be other parts in the grid that limit the current. So in this case, the cable was not the limit. You can also have the opposite of the additional rating that you can have. This is an example of a very recent example of a wind farm with 2 cables. The online monitoring system that was installed saw that there was a thermal problem on both of the cables, and it was found out that it was due to a very unfavorable thermal resistivity of the soil. It was completely dried out. And that's prevented quite a big fault in both of the cables. And at the moment they can use it to limit the production to the maximum temperature. So this is just a recent example what it looks like. There was a period of time where there was not a lot of wind, so the cable cooled down. But then there were, for a long number of days, there was a high wind on the wind farm. And at one moment they had to limit it to in this case, 80 degrees fiber temperature, which then is the 90 degrees conductor temperature. But we can be pretty sure if they wouldn't have limited the cable, they're far off the design limit of the cable. So they both probably would have failed in that case, and it would have cost a lot of money to do the repairs, and also the missed revenue on the production. So this was a very good example how dynamic cable rating or real-time thermal rating prevented a failure in the power cables. The last example I wanted to show is a 150 kV connection from a TSO with only one circuit, where also indirectly was a lot of offshore wind connected to. There was a problem, also a thermal problem, only on a small section of about 10 meters, which was not understood fully. It was found out that the ducts that were used were not filled with bentonite as was expected, but only partially, and the rest was filled with air. But also induced currents in the external earthing cables also reduced the ampacity of the connection. This is the example of the cable that was dug up, and it was found out that inside of the duct where the cable was installed, there was a small layer of air, and for the rest it was bentonite. Normally when you install cables in ducts which are placed in air, you have some kind of convection, but in this case there was only a small layer of air, which is a very good insulator. So that was quite a thermal problem in this connection. And here you can see the load on the cable at that time. In orange you see the fiber temperature, and in this case the 75 degrees fiber temperature corresponded to the maximum conductor temperature, 90 degrees. So at this point they had to take measures to limit the cable to prevent any damage. So these are just 3 examples of how DCR can be used in underground power cables. You can use the transport capacity in a much better way, because you know the temperature, you know the actual ampacity of the cable, but it can also be used to prevent cable failures.
Unmuted.
heating. And yeah, in that case, when you have some problems in the grid, or you expect some problems in the grid, but you measure it and there will be no problem, then you can postpone or reconsider your new investments. Really, the biggest bottlenecks that we have seen is with the offshore wind, but more recently there's also the big solar solar farms that can give some problems due to the high peaks during the afternoon. So that's basically the presentation about dynamic cable rating.
Many thanks to you, Jozua. And I think we should have, let's say, updated the title of your presentation in seeing that you focus on, of course, the underground cables. Yeah, and it was interesting to see there is certainly a difference in maybe also the efficiency and opportunities for dynamic line rating on overhead lines. I suppose there are more, the variations in temperature are maybe higher than in underground. You didn't say that, but it's what one could maybe imagine. This is a question to be kept. Maybe for the end, is DLR more interesting for overhead or underground lines? Can already get prepared, both of you, for discussion. I'm happy now to have Victor Maire, the planning engineer from the National Control Center at Elia. Victor, you are the operational planning engineer, as I said. You are notably responsible for the implementation and the operational use of DLR technologies at Elia. One example was mentioned already on these AC offshore cables. You have a master degree in physics from Université Catholique de Louvain in Belgium, and also a joint degree in economics from UCL and Università Luigi Bocconi in Milano. So very happy, Victor, to have you here. And we are keen to understand what applications DLR has today in the world of the TSOs.
Yeah, good afternoon, everyone. So I'll go directly in the subject, and I hope I will answer all to your questions. So this is really important, I think, to mention. It's a little bit the history of the collaboration and work with Ampacimon, because this shows a lot about how you implement such fantastic technology. Because when you look at the theory, it's indeed incredible. Because in a few slides, Frederic showed you that you might gain 50, 100% capacity on an overhead line, which costs millions of euros to build. And this is a bit a dream technology for an operator of a grid. But also at the same time, when you see the numbers, you say, no, that's not possible. I mean, this is I don't believe it. I'm not ready to put the risk at stake for my grid. I need to be really sure that this theory is also viable on a real life. And so that's why it was a long process. We started really at the beginning, 10 years ago, with prototypes and in situ tests. And 3 years later, after several iterations, I was not even there at that time, but we decided to equip two lines. That was two lines really congested by wind in feed. We already heard by the previous speakers that it was a lot of problems due to winds. This is a typical problem for grid operator, and this technology has a virtuous influence with wind, because if you have a wind congestion due to wind and feed, automatically you'll gain more capacity thanks to the DLR. So that's always a good way to look at which line you should equip. And we decided only to equip those two lines, even though we had validate the whole process. For us, for Elia, it was safe to use the technology, but nonetheless we didn't make this big choice to install it on more lines, because we were still a bit afraid as any TSO. So it was only two lines, and now after 3 years of good working, we witnessed that the IT side communication also were really robust. The data we were using were correct, and we could verify ex post that everything was correctly working. That was a good positive message. Nonetheless, that was not for TSO. If it's not necessary, absolutely necessary, you will maybe not use it. But in 2014, the situation in Belgium was really critical. We had the problems with nuclear power plants, and so adequacy issues for the coming winter. And that was a big trigger for us to say, okay, we have tested this technology since now 6 years time. We know it works. Let's go a step further because we really need it. We need this extra capacity, and we installed on a dozen line DLR Ampacimons, notably as Frederic on the borderlines to increase the maximum import capacity of the country, because that was the problem at the time. Yeah, later on a new product. Also there, we didn't want it to install it directly. That was the forecast license. So it allows you to have an insight for the 2 coming days over the possible capacity you could have on those lines. And of course, this is really interesting for the market side. You know, if you can increase the capacity of your lines 2 days ahead, this means you have time to implement this on your grid and to give this to for us, for the flow-based market coupling or for other system, but you can give this input to the market exchange, and so you can optimize the exchange between the countries, and that's really valuable. And again, there it's only 2 years later, end of 2016, that we started to use this technology because we had enough confidence in it. And also there, we didn't want to use the entire forecast given by Ampacimon, because we're still, we need to manage the risk. We are TSO, we cannot give to the market too much margins if we're not really sure that we will have this margin on the real time. And so we make analysis to be really 99.9 sure that the gain given to the market will be available in real time. And we came up with those 2 capping, 105% during day, because this year the capping is lower, because typically the gain of Ampacimon is lower around midday, because you have solar, you have irradiation, you have high temperature, and so you're closer to the limit of the static rating, and so you're taking more risk. But at night, typical irradiations. So those capping levels were calculated and are used since this time now. And then each year we are increasing this technology on our grid. And today we have about 30 lines equipped. And basically all the equipped lines are the more critical lines, the more useful, the more loaded line. So we could say we really embrace this technology as something totally business as usual now. We have now the department grid development, so the long and mid-term overview over the several years ahead, who is also detecting the need for the coming years. And we are now really equipping all the lines when we see a good business case. This is an overview of the really high level of the grid of Elia, and you see directly that all the big lines. This is a 400 kV network mostly, and you see in purple that the big axis between Netherlands and France has been equipped and to release all the market exchanges, because the purple is the license for 2 days ahead. So it's also for the market, for the real time and for the market. In red, it's the license only for the real time, because there were no real added value to increase for day ahead, 2 days ahead, the capacities. You see also the offshore park and the red lines. You see two pairs of line equipped with the Ampacimon. This is the 150 kV, and that was really useful because we installed wind capacity before developing our grid properly. In the meantime, now we have a big 400 kV grid up to the coast, and the problem is not there anymore. But that was a temporary period, and Ampacimon is often a really good technology for temporary situations. Actually, for Elia, it's not a solution for a line for its lifetime. It's just you identify that for a few years' time you have a problem because you have too much capacity and you're busy to develop your grid. But in the meantime, your grid is not big enough. So this is a way to cover this temporary situations. And also, if you are doing great big works on your grid, you're weakening your grid, and so during the outages, you can just install capacity on the parallel line to avoid the problem on the grid again. So this is temporary situations, but it's really helpful. So that's how we use it. Of course, DLR, Ampacimon at least, is looking at the conductor. So really the overhead line conductor, but it's not supervising the whole chain. So you have to be careful with this also. For example, if you increase the current, because the sagging in the water temperature is okay, you will also potentially increase by high amount the generated heat. You will operate your line closer to the limit. This is a valid limit. You're not overloading your line. You're not going above the agreed and legal temperature, but you're exploiting your grid to its physical limit. So you have to be sure that all the chain of your the line's ends and all your overhead line has no hotspot is really good. The maintenance on the line is really well done. So that's why for those assets we changed the maintenance policy to prevent any further problem, because we know those lines by definition will be more loaded than an average line, and so you're using your asset at its limit. You're aging it a little bit more quickly. But if you have a proper maintenance policy, you will cover this aging problem, and actually you can maintain your asset as any other one. So we are doing a bit more preventive maintenance, more thermal visions to detect eventual hotspot, and more visual controls of the whole lines. Also the bus bay, you cannot forget those bus bays, and this is really important also. If you increase the conductor capacity, you have to be sure that the bus bay might cope with those higher loads. And so sometimes you have to make some investment to replace or upgrade the line ends also. You also have to adapt the protection because sometimes you will see higher current and you have to adapt the set point of the protections. This is mostly software, but you have to also think about it. So in practice, you have more steps than just installing a little box on the line. But if you do it properly, you will manage all the risk and you will be in control of this technology. And also, for this, at Elia side, we decided not to go as far as Ampacimon would allow. For example, if the wind blows in the good direction, you have seen from the presentation, Frederic, it is totally acceptable to double the capacity of a line. But this is something we are not ready to do because of this slide. I mean, you need to be quite reasonable also in the capacity you're ready to give and to use, and so it's a risk management. At Elia, we decided that 30% extra on a line is already a good one. I mean, 30% on a 400 kV line, that's a massive gain. That's something Ampacimon will give on average really a lot of time. So this is something you will have most of the time. Certainly in the winter situation, actually for Elia, it's always in the winter we always have this 30% gain. But we decided to limit ourselves to 30%. But this is up to the TSO to manage its own risk, of course. And this is just to show you in real time in our SCADA system. You see all the lines are equipped, and in the yellow box you have the Ampacimon gain, and this is automatically replaced by the static rating. So the dynamic rating is replaced. The static rating is replaced by the dynamic rating constantly, continuously, and the N-1 analysis, the security analysis, is done with this value. So we are totally trusting the technology, and this is fully automatic. So for the operator, it's manageable also, because he has 30 lines with that has to be automated. So the line might be in overload with respect to the static rating, but the dispatcher might not see it because Ampacimon says this is fine, you have enough margin, and so it will not be polluted with a fake incident. So that's how we do it. And then I'd like to finish with a concrete example. This is from 2017, but in the meantime, I have a dozen of this, but this one is really easy and nice to present. So that was today a typical day in the Belgian network. We had international flows going from the Netherlands towards France, and this was loading some lines on the way around, internal lines. We had to adapt the PST, the phase shifting transformer. We had 4 of them at the border, and we had to reduce the taps to a 6 position. 6 position is already really low because neutral position is 18 and lowest position is 1. So in day ahead, we had already to go to this situation for the 4 PSTs, 6, 6, 6, 6. And we also had to optimize the grid with all topological measures we could find. But we saw that in real time, so when the situation really happened, the line were still really highly loaded. And the only way to cover this, because the PST were also reduced to their limits, the only way to go further was to pay for international redispatching, which means we had to pay the Netherlands to reduce the power plants and the France to increase the power plant. This cost, for sure, without any calculation, $500,000 for this situation. This is a rough estimate, of course, but this is the most costly remedial action you can find. It's international redispatching. And thanks to Ampacimon, you see it on the graph. You see in green the loading of the critical line. You see in the night that the line were really close to the blue horizontal line, which is the static rating, which means automatically that there were an incident on the grid. After the incident would overload the line. You see it's so close to the static rating that is, of course, the N-1 was not covered with the static rating. But thanks to Ampacimon, you see the red curve, and you see also this beautiful effect that you have more margin in the night than in the day, and so the red curve was really capped at 30%. That's the rule I just explained. At Elia, we decided to cap the gain. We don't want to give 50% or 100% on the line. 30% is enough for us. You see that was saturated, so the real-time Ampacimon would have given even more. But thanks to this, we comfortably make it to this day. We still had to make a lot of topological actions, but we didn't have to pay anything, and the situation was totally safe for the grid. So that's one example among others. And when you compare the cost of redispatching to the cost of the technology, in one such a day, you just pay the license and installation of the technology of one line. So it is really difficult to have a good estimate of the gain you had over a year time, but you can easily find example where you won a lot of money. And so after those examples, it was really convinced for us, Elia, to continue with this technology. So that's about it. So well, I think I already said this. So the conclusion. So for me, I'm fine with the presentation. Thank you for your
Victor.
attention.
Now we have a bit of time left for questions, and I would like to ask the first question to Norela Constantinescu, who is leading the research and development work in ENTSO-E. Norela, what is the role, or what is ENTSO-E doing on dynamic line rating in the research and development committee, and what is the perspective that you see for this technology in our TSO world with 43 members?
So we look into this technology from a TSO perspective, so which means the application perspective. We have actually developed a fact sheet around this technology, which should be easy understandable by everybody else, so not only by TSOs, but maybe other participants who are in this webinar. So we have actually looked into how many TSOs are using this technology. It's quite largely used. So we have probably in 2015 we had 11 TSOs using this technology, and I suppose that today we have even more. We have also research and innovation projects, and one of them was mentioned by Guido in the introductory slide. It's called Osmos, and actually there is a demonstration in Italy, so in Terna, which is taking place. But of course, we as an association, we would like to see also the inputs from people like Frederic or like Jozua regarding actually how we can increase actually the use of this type of flexibility sources for the power system in terms of ampacity gain, as well as in terms of actually embedding into other type of tools that TSOs have, and how we can value these. And this is a question we have many times from the regulators. So I have seen that Acer is also present in today's webinar. So which will be the savings we have by using this technology, monetary saving, I would say, over a year.
Mm-hmm. Many thanks, Norela, for this overview, and this leads already to actions beyond today's webinar. Yeah. So I would like to bring from the many questions that we have received and that will be answered also by our distinguished speakers in a written manner. Yeah. I'd like to ask you the question that was asked most, and that is about the costs and the perspectives of dynamic line rating. From your presentations, you could get the impression that it's up and running. So what is coming up? Is it that with more renewables and because of the congestion costs and the redispatch, etc., and curtailment, it becomes even more interesting? Is there a scaling up effect? And maybe also what you expect from ENTSO-E on these kind of technologies. It would be interesting to have everyone's views on this cost and perspectives for a dynamic line rating. Starting with Frederic.
Yes, thanks, Susan. So in terms of cost, indeed, I had many questions that point to that. It's difficult to give a precise answer because the cost of the system would depend on the length of the line, because the longer the line, the more sensors you need to have. But what I can give you is an order of magnitude. You know, typically it's a few €100,000 per line. That's the sort of cost that you should consider, including the sensors and the software and the integration into the SCADA or EMS. So that's what typically you would be considering. As to what needs to happen to have this technology deployed on a larger scale, I think we are already seeing that now. We have several TSOs who have launched or are launching public tenders to equip a large portion of their grid. So we are not into pilots anymore, at least in Europe, and in some developing countries actually also moving pretty fast. So I think we have now reached the tipping point where this kind of technology is about to be deployed on a large scale. And I think the biggest hindrance to deployment, they were and they are still in many countries regulatory, but that's being taken care of gradually in many countries. But there were also about systems integrations. You know, dispatchers typically don't like to have yet another screen on their desk and another set of data to look at. And I think what Victor showed is that now these systems can be fully integrated into SCADAs and EMS so that it's actually completely transparent to the operators who doesn't see the difference between operating in the normal, usual way of static rating and operating in a dynamic line rating environment.
Many thanks, Frederic. Jozua, what's your perspective?
Yeah, in terms of costs, I can also not give you exactly numbers, but it's in the same range as with overhead lines, I would say. We've already installed a lot of these systems, so I could say it's already accepted by some TSOs, but also wind farms. Sometimes they even take dynamic cable rating into account during the design, so they can choose a smaller cable in combination with DCR, because the wind is not always there, and sometimes there is a low load, and because the time constants on underground cables are pretty large, so you have a lot of thermal capacity to use, and that's one of the main differences, I would say, with overhead lines. And one of the challenges sometimes with implementing the systems is that to combine it with the SCADA system or a TSO to get the data to the right screen, that's sometimes a challenge. At some TSOs it's more easy than others, and for wind farms it's the same. So SCADA implementation is something that's important to take care of.
Okay, it's very also interesting to ask the question, the cost that Frederic mentioned, some few 100,000 per line average, if this is offset by the costs that we see on the congestions, that would be certainly interesting to understand. Maybe Victor, you can answer that question, and I would like to add for you, Victor, a bit of another question. You were mentioning that you at Elia are limiting the use to 30% because you don't want to go into risk. Would you be able to specify what kind of risks are you talking about in going beyond 30?
Yes, I think because the first part of the question I already answered it during my presentation, but for the risk part, so the 30%, I mean, this is more. I mean, you have on you as an operator, a grid operator, you have different kind of assets. You have old assets, you have new assets, you have different standards because it's evolving year after years. And for some lines, 30% is already a lot because it's an old asset, maybe 30 years old. So you might have not a perfect junction in the conductor. You might have some local problems on your assets. You have to maintain it every year to be in a good shape. And so for those assets, you don't want to make 30% is really good. For a new asset with a bus bay with really high levels, you could say maybe 30% is too conservative. I can go higher. But for the moment at Elia, we just said 30% is for all lines. So for the old one, for the new ones, and so this way we're sure that we're not taking risk for the old lines.
You could, if I get it right, you could beyond for the new lines, right? You could potentially go beyond.
Yeah, I could change. This is a cap. TSO can decide. On theory, the theory is there. You could you could just tap the maximum capacity Ampacimon give. If the line ends and the bus bay allows this, on paper, this is fine. But even though it's fine technically, exploiting your grid at its physical limit, if you put all your lines at 70 degrees, this is fine technically, you can do it. You're taking more risk than if your lines are 50 degrees. So you're not overloading those lines, but you're more close to the limits. And if you're close to the limits, you're aging your assets, you're automatically taking more risk.
Mm-hmm. What about
disconnection of hotspot?
Victor, what about cybersecurity? Is there a risk related to that, given this?
Yeah, that's a good question. So, because it's a new decision, we had also this technology is now so massive for us that it has become a critical situation, a critical technology. Because if now I lost the connection of the system dealing with all the data, and in my SCADA, I should in 1 minute go back to the static rating for all those 30 lines, and might be in a critical situation. And so this is something we should avoid at any cost. That's why also we decided that all the system that is dealing with this data should be developed and has the same criticality as the SCADA system. So for cybersecurity, that's fine. You cannot have any breach and so on. Any link that could be a weakest link, but in the whole history of our partnership, we never had this problem, but it's the antenna of the telephone, the phone network, because we're using the phone network to communicate the data in real time. That is the technology of Ampacimon. So if Proximus or any other provider for the phone network has some issues, then we could lose indeed the data. But we practically never had this issue. So that's why also progressively we built up a confidence with the technology, and we step by step, years after years, we increased the installed lines.
Mm-hmm. Yeah. Okay. So many thanks. Yeah. Go, please. Yeah.
Yeah, so I just wanted to add to Victor's reply on the cybersecurity risk. It's indeed something that utilities are more and more sensitive to. As far as we're concerned, we've deployed a lot of embedded cybersecurity layers into our software, the communication layers, and the processing software, and we have it audited by external partners to provide as strong a guarantee as we can that our systems are robust in that. In that sense.
Thank you very much for this complimentary response. I think the elements of your both responses to a topic that will be addressed in a separate webinar, show it's most probably more than addressing one element separation, but the cluster of elements. We see that also in e-mobility, this kind of Internet of Energy things that's emerging, or new software layers in our architectures, that deserve all our attention and are addressed in many places, and indeed as well in ENTSO-E. So I'm extremely happy for this very interesting discussion today, and would like to thank Frederic, Jozua, Victor, Guido, and Norela for this very interesting contribution. You will find the answers on those questions that you asked on the website of this webinar. I would like to thank as well Joanna, who is our really person ensuring that these webinars are going right. And maybe, Joanna, you can announce already the next one.
So we are very happy to welcome all of you on the 24th of April on a webinar that is talking about AI, artificial intelligence, and electricity. Yes. We will be discussing satellite technologies and smart grids.
Yes, exactly. So that's the next one. And then ENTSO-E is working with the ESA, the European Space Agency, on several things. Be surprised, 8 months ahead of Christmas, 24th of April. So thanks again to the team here, to Laurent, to Valentina, and to Joanna for making this happen. And thanks to all those who have listened to our webinar. Thank you. Bye-bye.
Thank you.
Bye to everybody.
Bye.